Welcome to Engineering Simple. In this video, I'll be talking about transformer testing, in particular zero sequence impedance with respect to grounded Y transformers with a buried delta, or also known as stabilizing winding. So this is part one. I'm planning on doing part two on grounded Y without a delta, and possibly doing a delta a grounded Y, and then probably a shell form autotransformer, which is grounded Y. Just to kind of see the difference between the different connections. So this is an important concept, especially for those in power system protection. So transformer zero sequence impedance and how it relates to positive and negative sequence impedance. So the positive and negative sequence flux path is the same. The magnetic path for zero sequence flux is typically different from positive and negative sequence flux path. The negative and positive sequence flux cancel each other due to the 120-degree separation of each of the three-phase flux. So if you take a three-phase, for instance, core. So if we assume this is a core, so this is kind of the middle leg, and obviously the coils are somewhere here. Are wound around the core limbs. And for core form, the windings are cylindrical. So you have the core limb, then the low voltage, then the high voltage, and they are cylindrical. So if you induce the high voltage, for instance, if you apply voltage to the high voltage, it will induce voltage in the high voltage winding, which will cause flux to flow, magnetic flux to flow in this limb, for instance. The same thing here, the same thing here. So, and as these kind of, if you think about like circuits like KCL, and this is an analogy. Basically, these fluxes will cancel here because they are separated by 120 degrees. So that's why for positive and negative sequence fluxes, you don't need the returns or the magnetic returns. But anyway, the zero sequence flux is different from the positive and negative sequence flux. So zero sequence impedance for three-phase, three-leg, or three-limb core is about 85 to 90% of the positive sequence impedance. Zero sequence impedance of five-leg core is about 90 to 100% of the positive sequence impedance. Shell form, typically it's almost the same as positive sequence impedance. So these are just kind of general observations. So in the following slides, I'll provide a calculation example of zero sequence impedance, and then kind of how to build the T model, the equivalent T model of a three-phase, three-leg core transformer connected as a 27 MVA, 138 kV grounded Y on the high side and 12 kV grounded Y on the low side with a buried delta, or also called stabilizing winding. So it's called buried because the leads of the windings are not brought out. So this delta is not serving load or anything. It's just there for third harmonic suppression, and also for handling zero sequence currents. And I'll stick with the industry terminology. So IEEE calls it stabilizing winding. So there's a difference. So there's stabilizing winding and there's a tertiary. A tertiary winding, it's also a delta but it serves loads. That's the difference. Stabilizing winding does not serve load. So some notation. So the high side, I'm going to call the terminals H's, like H1, H2, H3. Low voltage, I'm going to call X. So X1, X2, X3. So we have three phases. Some may call, instead of X, they might call it L for low voltage. So, but for me, I'll just call it HX. And in the stabilizing winding, I'm going to call it Y. If you read a book or a textbook, or probably you attended a webinar or something, you might also hear T, kind of referring to tertiary. So the high side is 138 kV line-to-line voltage. The low side is 12 kV, and the stabilizing winding is 6.93 kV. So the base MVA of the zero sequence impedance is the MVA rating of the excited winding. So as you will see in the following slides, there are like multiple tests are applied to come up with the zero sequence impedance, and each time you apply voltage to one winding, either the high side or low voltage side. So the base MVA of the zero sequence is for the winding, the rating of the winding that's being excited. And for power system analysis, typically 100 MVA is used. So T model. How do we build a T model of a three-phase transformer from test data? And the following slides will show the calculation. But basically, you have the H terminal, the high side, and you have the low voltage side, X terminal, and here's the stabilizing winding, or terminals, or Y. So from here, so this here, you would provide the zero sequence of the high voltage winding, zero sequence impedance of the low voltage winding, and this is the kind of stabilizing winding, the zero sequence of the stabilizing winding. And as we'll see in other future videos, if you don't have a stabilizing winding, basically this would be the tank, because the tank acts like a phantom delta. And I'll provide information on that in a future video. So basically this is how we build the T model, and we'll see how we come up with these values here. So someone might ask, why do we need the T model? Power system protection engineers need all sequence components to calculate short circuit currents properly. So what I'm showing here, here's the positive, so I'm just going to write sign, plus sign, so positive sequence network, here's negative, and here's zero sequence. So as you can see, positive and negative are the same, with the exception of the negative sequence does not have a source, because there is no source. So there is no source. Positive sequence has a source. But look at the zero sequence. In order to model it properly, you have to include the T model. That's very important. So what I'm showing here, so for the positive sequence, actually, I can go to the next slide and kind of redraw it just so to eliminate any confusion. So the way you draw it, especially, so this is for line to ground false. So you draw basically the source, then you draw the system impedance, then the transformer impedance, the high side, then the low side, then the other system. So this is 138, this is 12 kV, or whatever voltage you have. So this is the neutral. So I'm just going to call this V1 positive. One is basically positive sequence. So I'm just going to call this Z1, meaning positive system high side. For instance, this is the transformer. So I'm just going to call it Z1H. This is the low side. So I'm going to call it X. This is the system, but these system are two different impedances. So I just don't want to cause confusion. So this is basically as seen from this side here, and this as seen from this side. So two different voltages. Then for negative sequence, so basically you draw the same sequence network with the exception there's no source. So here basically you just rewrite the same values. So if you don't have any rotating machine, the positive and negative sequence impedances are the same. So I'm just gonna avoid writing zero sequence system on the high side just for simplicity. So this is negative sequence. Two just means these. Two just means negative sequence. So some people might write 0 for zero sequence, 1 for positive, and 2 for negative. Others might write 0, 1 instead of 1 plus meaning positive, negative sign for negative sequence. So it depends. They all mean the same thing. So this is the system. So like I was saying, so this might be like in our case 138 kV side. This would be the 12 kV side. So then for the zero sequence, it's a little bit different. So you write here's the zero sequence of the system, transformer high side, low side, then the system. But then you have to show the stabilizing kind of branch. So basically zero sequence of the system high side, zero sequence, system, and this is the Y, or the stabilizing winding. So I'm going to pick a different color. So basically here, so this is the T model. So it's very important. That's what you would get from the transformer test report. So the way you connect these sequence networks is a different color. So you take basically the neutral of this side, you connect it to this side. This is assuming there is no no impedance, from between the neutral and the ground. Obviously, if there's impedance, you would add it here. You would add 3 times. Let's assume this is solidly grounded, just for simplicity. So then why is the T model important? Well, let's start with here. So you have the source. So if you have a line to ground fault, so you have a line to ground fault. So the current would flow through these impedances, then through here. So some of this current here will flow through the stabilizer winding, and some of it will flow through here. So obviously, if you have a stabilizer winding, this impedance will be smaller than if you don't have a stabilizer winding. So this stabilizing winding has to be designed properly because it will see a lot of current. And there is a video that I made on this topic, like the importance of sizing the stabilizer winding properly. Because some people might assume, oh, let's assume infinite bus and just assume basically the system impedance is 0. So if you remove this here, that means most of the current will flow through here because you basically reduce the impedance. So you just basically are saying most current will flow through here. That mean, and that what would that do is it will cause the stabilizing winding to be undersized, which is a problem. So having the T model and also the system impedances in place is very critical. And these system impedances, the zero sequence system impedances, they can be from 3 to 5 times the system positive sequence impedance. Obviously, the further you go away from the source, the larger those impedances get. So they are very critical. So these impedances are very critical in the sizing or the design of this stabilizing winding and also the main windings when it comes to line to ground fault. So basically, kind of showed the sequence components, positive sequence, negative sequence, then zero sequence, and how important the T model is, and also including the system impedances, especially for the calculation of the line to ground faults that the main windings will see, as well as the stabilizer winding. So during the zero sequence impedance test, 4 tests will be performed, and these 4 tests are only if you have a grounded Y transformer, and because this is the subject or the topic of this video. So the delta winding, meaning the stabilizing winding, remains closed throughout the zero sequence testing. You don't short the terminals or anything, you just leave them, you leave the delta basically as is. So then single phase voltage is applied with obviously without exceeding the radians of any winding, because sometimes the circulating current can exceed the the withstand of one of the windings. So it's important to check, make sure that while applying single phase voltage, it does not cause exceeding the ratings of any of the windings, which would cause probably heating of the tank and other issues. So that's important. Single phase voltage only applied to windings with a grounded Y. So if it's a delta, you cannot apply the single phase voltage or ungrounded Y. So you have to have a neutral that's grounded. So now let's talk about the tests. So kind of a reminder, these 4 tests are only if you have a grounded Y, So let's keep that in mind. Because if one side is ungrounded or it's a delta, you only apply one test. That's the topic of a future video, delta Y, delta grounded Y transformer, zero sequence impedance. So how do you, so this is test 1, and this is kind of defined by industry, IEEE, and so on and so forth. So for me, I'm going to call it T1. So anytime you see T1 reference, it means test 1. So you apply single phase voltage to the high voltage winding. In this case, which I'm demonstrating, just because it's always good to go to explain a topic through an example instead of just giving vague or broad information, which can cause confusion. So then all 3 high voltage windings are shorted. In other words, they're connected in parallel. Low voltage windings are left open. The stabilizing winding delta remains closed. So here's what I mean. So basically you have the high voltage. So these are the terminals, H1 or bushings, H2, H3. Then you have the low voltage, the same thing, X1, X2, X3, and you have XO. Then you have the delta, the stabilizing winding. So what you do, basically you short the high voltage terminals, then you apply single phase voltage from all the shorted windings to the HO. In this case, so originally the HO will be grounded, or the HO bushing will be grounded. But since you're going to apply this test from all the windings shorted to the HO, this will need to be ungrounded. So the low voltage winding will stay open, basically just as is, except XO will be grounded. So that's what I'm showing here. So you see here's H1, H2, H3, HO. So the red is basically the jumpers that shorts all the terminals, all the bushings together. So you see H1 is shorted to H2 to H3. Then you have a source from all the windings shorted to HO, and low voltage is left alone, delta is left alone. So here's the measured voltage, 1.638 kV or 1638.2 volts. The measured current is 35.81 amps. So this is how you calculate the zero sequence impedance. So let's say in ohms. So it's 3 times the voltage, the measured voltage divided by the measured current. So 3 times 1638.2 volts divided by 35.81 amps, which comes to 137.24 ohms per phase. Notice I multiplied by 3 here because the voltage that's applied is per phase, and the current that's measured, it's 3 times because you shorted all these windings in parallel, so it's 3 times. So that's why there's this multiplier here, 3. So now the zero sequence for test 1 is 3 times 100%. Basically, I'm just converting to 100% times. So you have a quantity here, the measured voltage divided by the measured current, quantity divided by another quantity. In other words, this is the actual, because it's what's measured. This is the base. And what is this? This is the definition of per unit or percent. So per unit quantity is the actual divided by the base. This is per unit. Obviously, if you want percent, you just do times 100%, then becomes. So that's what I'm doing here. So the measured voltage divided by the measured current, the entire thing divided by the rated voltage, which is divided by rated current. So 3 times 100% is just 300. So if I rearrange this, so measured voltage divided by the rated voltage times the rated current divided by the measured current. So I just basically rearranged this equation here. So what is the rated voltage? Since I'm applying voltage to the high side, so I'm using 138 kV. So 138 kV divided by square root of 3, it's 79.77 kV. Why am I converting to phase to neutral voltage? It's because I'm applying single phase, it's right here, apply single phase voltage. So that's why I have to convert to phase to neutral voltage. The rated current, since the base of the winding that I'm applying voltage to, which is a high voltage, is 27 MVA divided by 130 kV times square root of 3, which is 112.96 amps. So now basically I'm just going to plug the numbers into this equation. 300 times measured voltage divided by rated voltage, quantity times rated current divided by measured current. So 300 times 1.6382. So basically this is just what the measured voltage. And notice I put the units that way. I'm consistent in this, so I don't make a mistake, basically, so they are canceling out nicely. Divided by the rated voltage per phase, 79.77 kV. So basically kV cancel out, so I don't have to do any conversion. Times the rated current, which is basically, it's right here, 112.96 amps, divided by the measured current, 35.81 amps. So here is the zero sequence impedance obtained from test 1. So it's 19.43%. So then I do the same thing for test 2. So what is the definition of test 2? Again, apply single phase voltage to the high voltage, still the high voltage, except this time, well, still the high voltage windings are shorted, but the low voltage, instead of left open, this time they're shorted. So that's what I'm doing here. So you see the high voltage, you short all the high voltage terminals, then you apply single phase voltage. The low voltage in this case, they're shorted, but the delta, I don't do anything with it. So Delta remains closed. So the measured voltage is 1705.6 volts. The measured current is 60.92 amps. Again, the same formula or equation for calculating the zero sequence impedance. Again, 3, I'm multiplying by 3 because the measured current is 3 times, because all 3 windings are in parallel. So if I just plug the numbers, I get 83.99 ohms per phase. Because why is it per phase? So the voltage that's measured is single phase or phase to neutral. The current is basically 3 times. So it's like 3 times. So 3 divided by 3 is 1. So that's why it's amps per phase. So again, here's the formula. I'm just repeating the formula. And since I'm still applying voltage to the high side, so I'm gonna calculate the phase to neutral voltage of the high side, which I already did. So the current is still the same since I'm applying voltage to the high side. So the zero sequence obtained from test 2, basically the same formula, is just plug in the correct numbers. So I get 11.89%. Now let's go to test 3. So this is test 3. Still applying single phase voltage, but this time to the low voltage windings, so 12 kV side. All 3 low voltage windings are shorted. So that's we see from here, X1, X2, and X3 are shorted. And you see here is the single phase voltage is applied to the low voltage winding shorted to XO. The high voltage windings are left open, so you see they're open. The delta remains closed, so the measured voltage is 175.27 volts. The measured current is 790.32 amps. Again, I go through the same equation, I plug the numbers, I get 0.6653 ohms per phase. So again, this is just the same equations, except this time the rated voltage, since I'm applying voltage to the 12 kV side, so I need to convert the line-to-line voltage of the 12 kV side to phase to neutral. So it's 6.93 kV. The rated current is still 27 MVA, except the voltage is 12 kV, so 1299 amps. So then I just so the zero sequence obtained from test 3, so 300 times, basically I'm using the same formula, so I'm just plugging the numbers. So you see the rated current is here, the measured current is here, here's the rated voltage, measured voltage, and the zero sequence obtained from test 3 is 12.47%. Last but not least, test 4. Single phase voltage is applied to the low voltage winding. All low voltage windings are shorted. This time the high voltage windings are shorted. So you see the low voltage are shorted, then you apply single phase voltage. The high voltage this time are shorted. So red means jumpers, basically shorting the windings. So delta remains closed. So the measured voltage is 111.11 volts. The measured current is 799.91 amps. So if I plug in the numbers, I get the zero sequence in ohms for this test. Test 4 is 0.4167 ohms per phase. Then since I'm applying voltage to low voltage side, I convert to line to neutral. So the zero sequence obtained from test 4 is, if I plug all the numbers, it's 7.811%. So basically what you do, you start with the high voltage, you apply voltage to the high voltage. After you short all the windings, low voltage you leave open. Then you apply voltage to the high voltage windings being shorted, low voltage you short. Then you alternate low voltage with the high voltage open, the high voltage with, sorry, low voltage with the high voltage shorted. So you apply voltage to one winding with the other winding open, then you apply voltage to the winding with the other voltage, the other winding shorted, and you alternate. So let's kind of summarize. So we said zero sequence impedance obtained from test 1 is a measure of the impedance of the high side winding plus the delta, since low voltage is open. Basically, if I do a quick sketch here, so if I assume this is a high voltage, this is a low voltage, this is the delta. So what I did, I shorted the high voltage, then I apply single phase voltage to here. So what's involved in this case? So basically, so this is in the circuit, this is not in the circuit because everything is open. But since this is a delta, it's closed, it's in the circuit. So that's why it's the high side winding plus the delta. In other words, we can write the zero sequence obtained from test 1, T1 is just test 1, is the zero sequence of the high side, H is the high side, plus the zero sequence of the Y is the delta or the stabilizing winding, and this is the number. This is what I calculated in the previous slide from test 1. Basically, it's this number here. So I'm just summarizing. So, and just keep in mind this value on the transformer base. So in this particular case, it's 27 MVA. Obviously, if you want to convert it to 100 MVA, you can do that. To convert it to 100 MVA, you would take 19.43% times 100 MVA divided by 27. So MVA of the new base divided by the MVA of the old base. That should give you the 100 MVA on the value on 100 MVA base. So then the zero sequence impedance obtained from test 2 is a measure of the impedance of the high side plus the quantity delta in parallel with the low voltage. Let's do a quick sketch. So this is the high side, this is the low voltage, and this is the delta. Just erase the delta. Again, the high voltage is self-shorted. Then you apply single phase voltage. But this case, the low voltage windings are shorted, which means You are applying voltage to the high side, but then the low voltage is in parallel with the stabilizing winding, or so that's what I'm writing here. So it's the zero sequence of the high voltage plus the quantity zero sequence of the stabilizing winding, or the delta, in parallel with the zero sequence impedance of the low voltage winding. And this number here, basically what I calculated previously. What I'm adding really is just this equation here. Again, this is on the transformer base. So the same thing for test 3 is a measure of the impedance of the low voltage plus the delta. Again, because in this case, so you have the low voltage, sorry, you have the high voltage, low voltage, then here's the delta. In this case, I shorted low voltage windings, then I apply single phase voltage. I left the high voltage open. So basically you have X, the impedance from the X winding, and plus the Y winding, or the delta. So it's just a sum. That's what I'm writing here. This number here I calculated previously. Again, it's on the transformer base. Again, the zero sequence impedance from the test 4, it's low side winding plus the delta in parallel with the high side. So it's always helpful to do a quick sketch. That way you know what's going on. So again, I'm energizing the low voltage windings, shorted. This is the neutral. And this time I'm shorting the high voltage. So you have the impedance from the X side plus these two. The high voltage is in parallel with the zero sequence of the delta, or stabilizing winding, or Y. So that's what I'm writing here. This number I already calculated, so it's on the transformer base. So this, if you want, you can prove this equation here, but for now just trust me on this, and I'll provide the proof in a different video. So the zero sequence impedance of the stabilizing winding is this quantity. Basically it's 1/2 the square root of this quantity plus the square root of this quantity. So in other words, so it's either 1/2 of the sum, or just is equal to this, or is just equal to this, or equal to this quantity. So that's what I'm doing here. If you plug the numbers from, so basically this is test 1, the zero sequence impedance from test 1 times zero sequence impedance from test 3 minus the impedance, zero sequence impedance from test 4 times zero sequence impedance from test 1. So the numbers are calculated in the previous slides. If you just plug the numbers, so that's the impedance, 9.51. Again, for now, just trust me on this here, but I'll do another video on this derivation. So then from the previous slides, we know the zero sequence impedance from test 1 is just the sum of the zero sequence impedance of the high voltage plus the stabilizing winding, and I calculated this value here. So if I rearrange, I can calculate the high voltage, because this is known and this is known from this slide here. Then it's just a matter of plugging the numbers. So it's 9.92%. Again, from a previous slide, the zero sequence impedance from test 3 is the sum of the zero sequence impedance of the low voltage plus the stabilizing winding, and the numbers is that. If I rearrange, I can calculate the zero sequence impedance of the low voltage side. So just rearranging, plug in the numbers, so it's 3.26%. Just keep in mind, sometimes the zero sequence impedance of the low voltage can be negative, and it has no physical meaning. So now we did all these calculations to come up with this T model here. So again, if I go back to the previous slides, the zero sequence of the high side is this value here. Zero sequence impedance of the low voltage, or X, is 3.26%, and the stabilizing winding is 9.51%. So we went through all that trouble to basically come up with this sketch, which is very important in modeling short circuit. So just be aware that IEC or IEEE 571290-2015 refers to my previous notation as follows. So what I call ZT1, they call Z1 and O. Basically, it's open, because if you remember, we shorted one side and applied voltage. The other side was open as shorted. So for me, just for simplification, I call them T1, T2. So just be aware of these notations. They mean the same thing. And what I called ZY, or the stabilizing winding, they call Z3. ZH, or high side, is they call Z2. ZX, they call Z1. So just be aware. The notations are different, but the meaning is the same. So that was it for this video. Again, this was transformer testing the zero sequence impedance for grounded Y with a stabilizing winding or a bare delta winding. And if you want to watch more videos, I would recommend going to Engineer Simple, and part 2 I will do grounded Y without the stabilizing winding. Just kind of see the difference. That's it for this video. Thank you. Have a great day or evening or night. It depends on wherever you are.